I have a quick simple question because I don't know
Yep.
why, but I just can't wrap my head
Yep.
around it for some reason.
Yep.
1 second, and I'll get it all up. It's on lecture 2, so it's the very beginning of it, but I don't know why I'm stuck on it, but I am. Um,
Yep.
Let me share my screen 1 second.
Yeah. You can share it now, I think.
Cool. Can you see that there?
Oh, yeah, I can see it. Yep. There we go.
Cool. So pretty much, I'm just going through all the example questions and stuff. So
Yep.
it's find the image point UV, which is on the image plane, right?
Yeah, that's the image point.
Cool.
Yes.
So, how do I don't know how to switch tabs. Is there a way to move this? Oh, there we go. Cool. So then I had a look at the quick MATLAB, I guess, solution to it.
Yep.
I'm just confused on how you get to this section here, the U and then the V is equal to F times X over Z plus PX and stuff.
All right, sure. Okay, so if you can go back to, so they you know, the two sections, there are two ways of solving it, right? So you're talking about the first way.
Yeah.
If you go up and up at the very beginning, it called central projection.
This one here?
No, it's principal offset. If you go up, keep going up. Here we go. Sorry. Yeah, the next page as well. Next page, please. Yeah, here we go. So that's the central projection.
Okay, cool.
The central projection means if you have an XYZ in a camera coordinate frame, right?
Yep.
And then if you look at the 3D, sorry, the left figure is the 3D figure, right? And image plane, camera center, and the spin hole camera model, right? And if you look at the right one, the top right figure, so that is the the Y and Z plane, right?
Yep.
And you can see, so there are two similar triangles, right? The small one and the big one, right? They are similar triangles, right? And if you look at the small one, if you look at the small one, the Y value, that is, let's say that's Y, not V at the moment, right? Let's say that's small Y, right? And then small y is something we didn't know. We want to calculate it because it's on the image, right? And then if you look at from C to P, that distance, that is focal length, right? So from camera center to the image plane, right? And then if you look at the large triangle, and the Y is the capital Y. That's the Y coordinate of the 3D feature, right? And Z is from C to Z. That is capital Z, which is the Z coordinates of the 3D point, right?
Okay.
Then we have capital Y divided by capital Z is equal to small y divided by F.
Right. Okay.
And then after that, if you calculate small y, then small y is equal to F times capital Y divided by capital Z.
Oh, okay. Okay, yeah, because that makes a lot more sense now. Because I was wondering how there was just two, but that makes sense
right?
X is.
Yeah.
Okay.
That is the central projection, and then it's similar to the XZ plane, so it will be similar. So it got similar equations as well. Yeah. So that's the central projection. And then if you go to the next page, probably next page. Yes, that's the one. So central projection gives you the points that with the origin of the principal point, which is a P.
Right. Okay.
P is the principal point which intersect. I mean, there's a camera axis, so which is from camera center to the Z, right? Camera axis. The intersection between the camera axis and also the image plane, that is the principal point P.
Okay.
And normally a picture is the pixel values UV. It can't be negative. It can't be negative, right? Right. But what you get from the central projection is because the origin is on P, so they may be positive or negative. and we want to move it. We want to move it with all the UV values positive. Then we called it a principal point offset.
Right. Okay. Oh,
so that's why, so that's why we have plus px plus py.
Yeah, I think I'll just do a refresher because it's been so long. But yeah, that makes a lot more sense now. Okay.
It's good to ask this question because that's the, I mean, that's the fundamental things behind it, and it's better if you know
Well,
it.
exactly. Yeah. Yeah. And then I guess the second method, then, if I can get it up.
Yeah, second method.
They do the x1 over x3.
Yeah.
I've completely forgotten that again.
Okay. Yeah. Sure. I know. You don't use it normally.
No.
That's the thing. Yeah. So if you go to the, probably you can go back to the code, and I can explain it to you.
Oh yeah. Hold up.
Yeah, probably that's not that obvious, but I mean it's very easy to follow, I believe. Yeah.
Yeah.
So, I think that the projection is the line with small x is equal to k times p times capital X, right?
Yeah.
That line. Yeah. And then we just need to know what is k, what is p, what is x.
Yeah,
right?
which is already got.
K is so k is a camera calibration matrix. You give it already. Focal length 1, and principal point, right?
Cool.
Like something like this. And P is a 3x4 matrix. I gave it already in this case, since there's no translation. If the 3 point is in the camera coordinate frame, right? So it's a 3x4 with the first 3x3 identity. So it's given already. And the capital X is, you can see that it's X, Y, Z, and 1.
Yeah.
Saw that, right? That point, we called it the homogeneous point.
Okay.
The homogeneous point, homogeneous point means if it is 3D point, then it will be 4 elements. It will be 1 plus 1 elements.
Okay. Yep.
Right. So in this case, it's a 3D point, then it will be X, Y, Z, and something. And here we added 1, right? And get something like this. For a homogeneous 3D point, let's say the capital X.
Yeah.
If you time n, let's say n is not 0, it represents the same point. That's why we call it homogeneous.
Oh, right. Okay.
Let me tell you why. So if you times n on the capital X, then you will have 15n, 10n, 80n, and n, right? And normally when we convert it from homogeneous point into normal 3D point, we use the first element divided by the last one, which is x, the second element divided by the last one, which is y, and the third element divided by the last one, which is z. So in this case, the first divided by the last one is still 15 if you times n on it. So that's why we use homogeneous point. So which means if you have a homogeneous point, you times a non-zero value, and it represents the same point.
Okay.
Right. And then what you get from that equation, that's a small x, right?
Yeah.
The small x is the homogeneous 2D point.
Oh, yeah. Okay.
Yeah. And then when you want to convert it into a normal 2D UV, then you use the first element divided by the last one, then you get U. The second element divided by the last one, which is V.
Right. Okay. So so X gives you what was the matrix C again, or the?
That's the 3x1 vector.
3x1. Okay.
Elements.
So then you take the first element and then the third element of that 3x1, and then that gives you the U and V.
From 3x1 to 2 values.
Okay, that makes a lot more sense now. Well, that answers everything, because I don't know, I just hadn't done it in a while, and I was like, what is going on here? But
so it's good asking that, because homogeneous point used a lot in the camera projection.
Yeah,
and then
sure.
See that if you use the matrix formulation, then you use the 3D homogeneous point, and you're getting a 2D homogeneous point, and you need to convert it into normal to the UV, right? So that's the whole process.
Okay, awesome. Oh, thank you very much.
No worries. Yeah.
Lost the Zoom.
Yeah. Other questions? Do you have other questions, Samuel?
Me. Oh, sorry. I'm still yet to go through most of it. I've been through kind of the last ones, but they all seem to be okay.
Okay,
but
cool.
if not, I can always email you if that's fine.
Yeah, sure.
Yeah,
Sure.
sweet as.
Yeah, and
All right,
you don't
thank
have
you.
to wait here. I'm recording, so I will
Yep.
upload it. Yeah, so you don't have to wait
Okay.
here if you have questions. Yeah,
Sweet as. Thank you.
no worries. See you, Sammy. Okay, so Sonu, you are the next one, right? How's
Yeah,
everything?
yeah. So I have a question. It's
Yep.
about the lecture 9. So let me just
Lecture 9. Yep. So
let
Samuel,
me
so
just-
could you please like stop sharing the screen and the others
Yeah,
can
I'm
share?
just trying to find where the Zoom went on my thing. I've got
Yeah,
absolutely no
so
idea.
if you move your mouse up about to the very top, probably you can see some button or the button one.
I got nothing. I think I hit it for
Okay.
some reason. So
I don't know if I can stop it. Or probably like Sonu, you can try
Yeah.
share the screen and see how it goes.
yeah.
I can't share. No, I can't share it, I think.
Oh, here we go. There we go. I got it. Sweet. We're all good now.
Great. Thanks,
Awesome.
Sammy.
Thank you.
No worries.
Yeah, so can you see my screen now?
Yep, I can. Yep.
So I have a question about this activity number 3.
Yeah, we're reserving one.
So the first question is like you have share a code about this question. So
Yep.
code is here. So my
Yep.
question is about the value of lambda. So here,
Lambda. Yep.
yeah, you haven't given the value of lambda, but in the code, I think you have taken the value of lambda as 0.1.
0.1. Yeah, sure.
Yeah. So from where does that 0.1 value comes?
Yeah, that's a very good point. So first of all, let me explain to you what is lambda. Lambda, so there is an equation. If you go back to the slides,
Yeah, let me.
with the page with lambda, I think.
Yeah, I know. Yeah, it's the exponential to the power minus lambda t. So it shows
Yes,
that.
that's the one. That's the one. It's kind of like a damping factor. It's
Yeah,
we make it e dot is equal to minus lambda times e, right? So
Yeah.
the main purpose of having this lambda is we want every time we don't want to reduce the complete error, because I mean at every time you have error, right?
Yeah.
So what we want to do is, because we keep like online doing this control, right? So instead of directly reduce the error to 0, but we reduce a small amount of the current error and do it regularly.
Yeah,
So
in the
that's why we
steps.
have lambda. Yeah, that's right. So that's why we have lambda.
Yeah.
And normally lambda should be something smaller than 1, right? Because we want to reduce a small amount of the current error. So normally we choose like 10% or 20%, so which means 0.1 or 0.2, right?
So we can assume.
Yeah, so if it's not given, you can assume saying that I want this lambda to be 0.1, then something. If it is given, if lambda is given, you just use the given one. Yeah.
Okay. And the other question is, so here we have given the rotation matrix and the translational matrix. So that is yes. So where do we use these things in our code? Like they haven't been used here.
That's a very good question. I put it here. I put it there, but you don't have to use it. That's the thing. So in the visual serving, everything is in the camera coordinate frame. And when you look at some objects, you have some local UV observations, right? Have some local UV observations, and you just based on the current UV observations and the desired UV observations, then you're calculating the control, which are the linear and angular velocity of the camera, and that's it. So normally we don't use that information.
Oh, so we don't use that thing, yeah?
Right. So in the code, there's no, right? We don't in the code, we didn't use it, right?
But if like we have to do a hand calculation, like we did in the in that formula, like the k multiplied by RC and then X coordinate?
It depends. So that's a very good question. It depends like what information you can get, right? So in this case, we have the information projected onto the image already, right? And we only want to calculate the control of the camera itself. So which means we don't need the camera global pose. That's the
okay. Okay. And another question is, so it's about the hand-eye calibration. So in the lecture you told about like if the camera is mounted on our end effector, so you have told about that case, like what we do in that case, we do AX is equal to BX, so we do the relative pose. But the other case is like the camera is not mounted on the end effector. So in that case, can you give a little bit idea, like with the robot, you told like we see it with the robot base. So like, can you give a little idea?
Yeah. Can you go to the next slide?
Yeah.
Yeah. No, I think the slide's 46.
Okay. Yep.
Yeah, this is one. So this is a normal one, right? So when the hand is holding the camera.
The camera, yeah.
Right. And that's normal one. And why I pointed out here is because I want to show you the basic idea about how to do this hand-eye calibration, right? For example, if in this case, the robot is holding a camera and the camera is looking at the checkboard.
Checkboard,
right? Yep. And then when you can control the robot to move the camera, but the camera like keep looking at the checkboard, right?
Okay.
Yeah. And then in this case, you can have a sequence of the end effector pose, right? A sequence of end effector poses. This can be calculated from the forward kinematics of the robot, right? So when you move the robot, you will know what's the pose of the end effector, right? That is from the forward kinematics. Then when you move it, you have a sequence of those poses, right?
Okay.
And then when you move it, you can have a corresponding sequence of camera poses with respect to the checkboard because it's looking at the checkboard, right? So if you remember when we do the camera calibration, then we can get extrinsic parameters. Extrinsic parameters means the relative pose between the camera and the trackball, right?
Yeah.
Yeah. In this case, you have two sequences of poses. One is from the camera and the other is from the robot end effector, right?
Yeah.
Then in this case, you can set up this AX equal to XB problem because you have two corresponding sequence of poses for each of the sensor, right?
Yeah.
So that's the basic idea why we have this AX equal to XB.
Okay.
All right, then let's come back to the other question, to your other question. Can you go to the probably next page? I think that is easier. Yeah, this one is easier. This one is easier. So supposing your robot arm, your robot end effector is holding a checkboard, right?
Yeah.
And we have a global camera on the top right.
Yeah, it's here. Yeah.
Yep. And then we still like control the robot to move, right? Let's say it's moving. And then in this case, we have a sequence of robot end effector poses, right?
Yep.
And in the other case, because the global arm, sorry, still this slide, and from the global camera, because the global camera is looking at the checkboard held by the hand, right?
Yeah.
And it can has a sequence of the checkboard poses.
Yeah.
Right? And then you still have two corresponding sequences of poses.
Yeah, exactly.
And then you can still form the AX equal to XB problem.
Okay, I get it now.
And then you can get the relative pose between the checkboard and the end effector.
Yep. Yeah, I got it. Yeah,
okay, cool. Great.
Yep, thank you.
No worries. Other questions?
Yeah, that's it.
Okay, cool. Thanks.
Okay, so let me close it.
Yeah.
Just a second.
No worries. So Sachin, are you the third one? I don't know exactly the queue, so sorry if I make it wrong.
Yeah, I'm not too sure. I got in a bit late though.
Yeah, but probably go ahead first.
Yeah, sure. Yeah, so I was just wondering about what was it? Oh yeah, so for the for like finding some of the matrices like the A, B, and C matrices, for the let me just check the question. Hold on, can I get back to you in just a second?
Oh yeah, sure, don't worry.
Check.
Yeah, sure. Yeah, so probably we can go to Josh first. So Josh. So Joshua, do you want to?
I'm
talk
just
about
listening to people's questions, Liang. I don't have any
Oh
myself.
yeah, sure. Yeah, sure.
Okay.
But don't worry. So you don't have to wait here. I'm recording and I'll upload it.
Oh yeah,
So
I'm
you
just
can-
doing work
if you
at the
can-
same time, so I
Yeah,
can
sure.
ask a question if something comes up.
Yeah, sure. Yeah, no worries.
Yeah, okay, I think I found it.
Yep.
So it was some of the questions to do with forming the stuff for tutorial 7. So it was about like forming the different matrices, like the A matrix, the B matrix, and the C matrix. So going from a model of the system that's like described with words like in that tutorial we were given an image that had the different that like described the system.
The supply chain one, is that the one?
Yeah, the supply chain one.
How to formulate that, right? Yep.
Yes.
Do you have the material? You can share the screen, or you want me to share it?
I do.
I can share it if you want. I can find it. Where is it? It's in the linear discrete time system.
Yeah, it was tutorial 7, question 1.
Yep. Second. Downloading. My internet was pretty bad. Here we go. And where is it? The supply chain one, right?
Yep.
Okay, let me share my screen. All right, so here we go. So you can see my screen now, right? With the supply chain activity 2. So that's the question, right?
Yeah, so it was the tutorial question that was like basically the same thing. And I was just looking at the MATLAB code that's associated with it. And I was trying to understand how they created the A matrix from the system.
A matrix, right?
And
sure.
Is it that they started with a identity matrix and then they started adding or minusing depending on the direction that the values are going?
Yep.
It's just that when I tried to apply that to a different question, starting off with the identity matrix, it sort of looked a bit weird. Like, because with the example question, all the numbers are like 0.6, 0.1, and then so that when you have your identity matrix, which has like the 1, 1, 1 on the diagonal, it's like makes sense. But then if you have a question with different numbers and you start with 1, 1, 1, it's like it seems off.
Right, sure. Yeah, I think this is something about like how to convert these difference equations into matrices, right? Are we supposing that this differential equations, they are okay? So which means you can from the descriptions here, then you can formulate each of this equation. Is that okay?
Where does the ones come from?
This one.
Yeah, in each of the lines.
Yeah, sure. That's a very good point. So if we go for if we look at here, right? So this is x1. This is x1, right? So it says a fraction of delta 1 of the raw material is discarded, right? Something like this, right? And a fraction of alpha 1 is shipped to produce a P, right? So which means for S itself, it will get out of delta 1 times x1, right? And also it gets out a portion of alpha 1 times x1. That's clear?
Yeah.
Is that all right? Then what it remains in x1? Right. So x1 itself is 1, is x1, right?
Okay.
So which means x1, so the current what we remain in x1 is x1 minus alpha 1 times x1 minus delta 1 times x1 and plus u, right? Because u is getting in. So in this case, if you get the x1 out, that is 1 minus alpha 1 and minus delta 1. So that is why it is 1 there.
Okay.
But initially, it has 1, right?
Yeah.
And it gets an alpha partial out and a delta partial out. But so what it remains is 1 minus alpha 1 and 1 minus delta 1.
Okay, so I should probably, when I'm actually doing the question, I should probably formulate these equations first before I try and make the matrix, because then it's sort of makes more sense. Yeah, okay.
That's right. So yeah, always starting with this. So directly starting with the matrix makes things, it's very complicated. Sometimes I can't do it myself. So normally what I did is I just write those equations. Let's say we have like 3 states, x1, x2, x3, right? So I want to find a relationship between x1, k plus 1 and x1 and the others. And x2, k plus 1 is equal to what? And x3, k plus 1 is equal to what? So then because you have 3 variables in the state, then you have 3 this kind of equations. And then the next thing is you define what is your state. So normally the state is x1, x2, and x3, right? And normally we put it into a column vector, x1, x2, and x3. And then you try to formulate what is the A matrix, right? Then the A matrix times the x1, x2, and x3, then is equal to those 3 equations, but apart from the U part, right? So in this case, in this case, so normally the first row is telling you, so if in your first equation, there is a coefficient in front of x1, then you put it on the first element, right? And then because there's no like coefficients on x2 and x3, then x2 and x3, they are 0. That represents the first row of A.
Yeah.
And then for the second row of A, you did the same. For the second row of A, you look at the second equation, right? And then what is for x1? That is alpha 1. So you put alpha 1 in the first, right?
Okay. And then
you put the x2 one
and the gamma
and the third. Yes, something like this.
Okay, because then that means that the UK and the gamma x3k.
Yeah.
Wait, just the UK becomes separate, and then that becomes your B matrix.
UK becomes separate because I mean when you because it's AX plus BU, right?
Yeah.
AX plus BU. Then in this case, the B is 1, 0, 0, right? Because the second and third doesn't relate to U, so which means it needs to be 0. Right? The first one is U, then which means, I mean, if you use 1, 0, 0 times U, it gets you U, 0, 0, and represents the three equations, right?
Okay. And how's the C matrix formed?
C is something like this. So C is kind of like, what is your output? What is your output, right? So currently the output is something on the very right, right?
Yeah.
That is gamma 3 times x3. So in this case, your state is still x1, x2, and x3, right? And you want to have a C matrix that gets you gamma 3 times x3. So in this case, you will have a row vector, which gives you 0, 0, and gamma 3. And you use this row vector times the column vector x1 and x2 and x3, then you directly get gamma 3 times x3, something like this. So it's always starting with the separate difference equations, and then try to make it as the matrix format. And then a way to double check it is you times them out. Then what you get will be the separate equations you have. Then that's correct.
Okay. All right. So you can kind of think of B as like the input matrix and C as the output matrix.
Yes, something like this. Yeah. So
Okay.
probably have a practice on it, and probably you can get the relationship, and then you know how to do it.
Yeah. Okay. And so are there any tutorial examples for continuous? Oh, there is, because then you have to linearize. Oh no, that's for nonlinear. Were there any continuous discrete examples in the tutorials?
Sorry, continuous or discrete? They are different.
So in discrete, continuous linear systems.
Continuous linear system. We don't really have another one, but we have some examples. You mean formulations, right? So they're formulated from the real case into the system. This is what you mean, right?
Yeah.
Yeah, I think we have some in the slides, in the lecture notes. Where is it? Here we go. Yeah, it's very slow. Here we go. Yeah. Where is it? Where is it? Yeah. So I think we introduced the first one in the class. That is we call the simplified dragging system. That's similar to cruise control system.
Okay.
Right. Yeah, and how to formulate it from the physical model of the system itself, something like this. And then we introduced the mass spring damper system. This is a bit more complicated, and also you have two states in it. Then we convert it into a matrix format. But I mean, it's always like you start with this formulation and try to convert it into a matrix, something like this.
Yeah.
So
okay.
we have some more complicated one, but I think it's too complicated. That's why I didn't introduce it. So there are a lot of other like examples from this one. So that's a MATLAB one, I think, and you can try it.
Okay. Oh, and they come with the MATLAB solutions for them as well.
Yeah, I think so. Yeah, but I mean, okay. Don't start with very complicated one unless you really use it. You really need it. I think the more important thing is you understand like what is the linear continuous time system, and then you know how to formulate the real case into the linear continuous time system from the physical meaning. And I think that is more important. And then in the later case, probably you have some more complicated cases. Then you can think about that, but with your understanding about how to do it.
Okay, because the formulation of this is a little bit different because you have the state vector, right?
Yeah. So this one is very simple, right? So you only have like your state is only one, so you don't have a state vector, right? And then you start with the Newton's second law and to formulate it, and you choose. In this case, you choose like velocity as the state, and the v dot means the acceleration, right? Something like this. Yeah, and the other one again is still start with the Newton's second law, and then you have this formulation and you change it into here. But the problem is, if you can see, there's x, which is distance, x dot means velocity, and x2 dots means the acceleration. So in this case, if you have x dot x2 dots, sorry, x dot x2 dots, then probably you need to choose the state vector with x and x dot, right? Then the capital X dot, you have x dot and x2 dots. Then you can convert your initial formulation into this standard formulation. Yeah, try to think about how to convert it, and try to solve. Then probably you get it. So let's say you have this A and B, and put it here. If you put it here, then you will have this equation. Try to calculate it inside. So replacing x, replacing this x by x and x dot.
Like matrix multiplication, just
yeah, and then, yeah. After you do that, you will have this equation. Yeah.
Okay. Okay. So we should just know how to sort of factorize the matrix, like factorize an A matrix out of.
Yeah. So from the formulation you have.
Okay.
And from the matrix, and if you multiply them, and then you'll get back to this something like that.
Okay. And the point of using the state vector is to allow us to condense it into a matrix like that, basically.
Yeah. And okay. Also, like, because you have x dot and x2 dots, then if in this case, probably you need to change like a state vector with x and x dot. Because in the standard formulation, where is it? Yeah, it's like x dot and x. There's no x2 dots. So that's why here we introduce a state vector with 2, because this x2 dot, x dot, and x.
Okay. All right. And also another question for the linear discrete systems.
Yep.
If we don't get given like a UK value, so initial input, I guess, we can't really evaluate anything, right? We can't do any.
Sorry, wait a second. I think I closed it. Yeah. Sorry. Can you repeat the question?
For the linear discrete systems,
yeah,
if we're not given a UK value as the initial input, we can't evaluate the system for any amount of stages, can we?
Yeah, that's a good point. Yes, you're right. So you need to have x0, so which means the initial position of the state, and also the UK. So normally we need to assume we have those. Then you can evaluate the state at any time.
Okay, all right, that makes sense. Oh yeah, and for LQR as well. Out of the Q and the R matrix, which one was the performance and the effort one?
That's a very good point. So normally the two metrics we are given. So you didn't. I mean, if there is a question about that, you don't need to worry too much about that. So normally, like, those two metrics are given. So sometimes the two metrics they are given with some experiences, something like this.
Right. Okay. So let's say like, oh, set Q to this, and then evaluate, and then like what's the solution?
Let me go back to
Yeah. Okay. Instead of saying like, oh, set the performance matrix, it would be like set Q.
Here we go. Here we go. Yeah, I think the Q and R metrics, they are here, right? So it's in the Riccati equation. It's in the Riccati equation. Yeah. So the main purpose is we try to minimize the performance index, right? And how to do it is finding a K to minimize the performance index, right? And the first step is getting P from this Riccati equation, and from this Riccati equation, you need the R and Q, right? Normally it's given, yeah. And then from P you can get K, right? And from K you can get U, and that's everything. Yeah.
So you if we were asked to like solve the Riccati equation,
it's a good question.
it takes some time, doesn't it? Yeah.
I think we can solve it in MATLAB. Using LQR.
Yeah, that's right. That's right, Shenu. So if it is a long answer question, which means it is a calculation, then you can use MATLAB to help you to do that, right? So if it's not, if it's short answer questions, so which means I just ask you to describe the process about doing this, then probably you just need to write the step one by one and with the necessary equation, and that's it.
Okay, so like the equation that's right there, pretty much.
Yeah.
Okay. Yeah, because in MATLAB there's the LQR function, but that
yeah. So if I'm asking you to calculate it, you can definitely use that function to do it. Okay. I'm not asking you to solve the Riccati equation by hand. There's no meaning of doing it.
Yeah, because that'll give you, when you hand in the system and the Q and the R, that gives you the K value. And then, yeah, okay. But we still have to give like the equation you would need to use, and then just use LQR. Okay.
Yep.
Okay, I think that's all I have just for now.
Yep, cool.
Thanks for the help. Thank you.
No worries, no worries. Oh, right. So other questions?
I'm not sure if you mentioned already, but is there a way to get the solutions to quiz 2 at all, or?
Yeah. I think I gave a reflection on it already in the class. Did you ask the question?
I'm not too sure.
Yeah, I think there's another email asking this question. I replied already. So I did a reflection on quiz 2, I think in the review session of the lecture. But anyway, there's a record. I think still in the review session. I think it's in the previous semesters, but I mean the question is very similar. So probably have a look at that. If you still have questions, you can come back to me. Yeah.
Okay, cool. All right, thank you for that.
No worries. Yeah, so again, you don't have to wait here. I'm recording, but are you happy? I mean, if you're happy waiting here, that's fine as well. So probably I'll mute myself. I'll like switch off my camera unless like there are some questions. All right.
Yeah, sure.
No worries.
Just quickly again, with triangulation, the baseline, do we always convert that to meters? Or does it depend?
No, normally it's a good question. So if you use meters, then your XYZ is in meters. Okay. So if you use millimeters, then your XYZ is in millimeters because so that's the only part with real scale. Yeah.
Okay, cool. So would you recommend though just whacking it in meters instead? Keep it simple.
So probably just meters, I think. Just
meters.
Yeah.
Okay, sweet. Thank you.
No worries.
Non-linear discrete system.
Yep.
So in the case of non-linear discrete system, so the stability and the controllability part will be same as that of the linear discrete system, or is it different? Like we calculate the value of lambda and that should be between -1 to 1, and the controllability part should be like linear discrete system. So we have to check the rank of the BAB and A.
The controllability metrics, right? Yeah, sure. The short answer is yes, that's right. And but I want to mention a little bit more on that. First is the stability or the controllability is not applied to the whole nonlinear discrete time system. So how we can check that is because it's nonlinear, so complicated. So what we did is we first calculate the equilibrium points to find out where are the equilibrium points in the nonlinear discrete time system. And then we find one or some of the equilibrium points, we linearize the system at the equilibrium point. So the linearization can only be applied on the equilibrium points, right? So we did linearization, let's say on one of the equilibrium points. And after that, you have a linear discrete time system, which is the same as what you have before. So that's why we introduced the linear continuous, linear discrete, and nonlinear discrete, right? So we need some basic knowledge in the front. So in this case, after you do the linearization on the equilibrium point, then you can check the stability and controllability of that point, not the whole system.
And for the continuous system, so we don't have to worry about the continuous non-linear system, because
we didn't introduce that. Yeah, that's right. We didn't introduce that. Yeah. So normally there are, but I want to introduce the nonlinear discrete time system because it is more like happening in the real case. So so we didn't introduce that. I can promise there's no questions on that in the final exam. So there's no nonlinear continuous time system.
But it's all it is similar to it is similar to this case also. Like there also we do the linearization about the equilibrium point, and then we convert it to a linear system, and then we treat it as a linear continuous system.
So normally it's like that. It's just like the when you calculate the stability, the equilibrium point, it will be a little bit different. And also after you do the linearization, the stability criteria will be different.
Okay, thank you.
No worries.
Hey, Liang, if we get a question about calculating camera velocity, and the question has two focal lengths, which one do we use?
Yeah, that's a good point. Okay, let me try to get the slides of the video surfing. Give me a second. I'll introduce a simple way and also a theoretically correct way. Just give me a second. Oh. Sorry, the internet is pretty slow. Give me a second. I'm trying to share my screen. And here we go. Okay, so it's visual serving, right? So when we talk about calculating the, give me a second. Here we go. So let me give a very easy way to deal with it. So if you have two values of the focal length, normally we have it, right? Because I mean, the pixels they are not perfectly square. So in this case, if you have two focal lengths, you can just average it and just use one. That's a very simple way. And in the engineering point of view, it doesn't affect too much. All right, but if you want to make it very, very accurate in a very theoretical sound way, then when you calculate the small x, you use fx. When you calculate the small y, and you use fy. So everything related to small x or like u, then you use fx. Then anything with small y and v, you use fy. So both are fine. Both are fine. Yeah.
Okay, cool. All right, thank you.
No worries.
So for if there is a question in the exam about two focal values, can we just take the average of two and use one value? Is that fine?
You can do added case. I'm happy with both.
Yeah.
Sorry, sir.
Yep.
Can you explain the linearization of the nonlinear one? Because I need this, but I'm not sure about the next step. Like we have to determine the linear, discrete, or linear continuous.
Sorry, just confirming your question. So are you talking about how to do the linearization?
Yeah. Yes, sir.
Oh, okay, cool. Have you watched the video record?
Yeah, I watched it, but
still doesn't work, right? Yeah. Okay. Give me a second. Which one is it? I think this one. Let me share my screen first.
Thank you, sir.
No worries, no worries. Just give me some time. Oh no, this one. I need to find out the lecture notes and share my screen. Share my screen. All right, so you can see my screen now, right? All right, cool. So you can see my screen now. Just confirming. Yes. Okay, cool. Sure. Yeah. So first of all, the linearization is based on the equilibrium point, right? So you can't. I mean, you can linearize it at different points, at other points, but there's no meaning of doing it, right? Because I mean, the system is so complicated. We want to find the equilibrium point, which is like reasonably stable. Then we do the linearization on it and we control on it, something like this, right? So the first thing is, if you have a nonlinear discrete time system and you want to linearize it and assess the the stability, controllability, and try to use state feedback control, right? The first thing is you need to calculate the equilibrium points, right? And after you calculate equilibrium points, then you can try to do the linearization And I give the very brief one here about linearization, and suppose we have this standard formulation, right? So xk plus 1 is equal to fx and u, and yk is equal to gx and u, right? And then how to calculate the A, B, C, D matrices for the linear discrete time system is A matrix is the partial derivative of f with respect to x. F is this function, all right? And B is the partial derivative of f divided by u with respect to u. All right, and C and D, they are there as well. The C, D are related to G, the partial derivative of G, right? But the
sorry.
Yep.
So we have f function with the two variables x and u,
yep.
and G with two variables with x and u. So we just derivative with like variables like so.
Yeah, that's a very good point. Yeah, so probably I'll explain it a bit in details. About like how to calculate this Jacobian, we call it Jacobian, the partial derivatives. Okay, so here I think everything's fine here, right?
Yes, sir.
But just about how to exactly calculate what's the Jacobian, what's the partial derivative, right? Yes. Okay, so I mean before that, I want to mention one thing, which is those partial derivatives need to be evaluated at the equilibrium point. You see that, right? Need to be evaluated at equilibrium point. You can't evaluate it at any other points. Then how to calculate this? Let's say give example of A, right? So A is the partial derivative of function f with respect to the state x, right? So let's give a very simple example. Let's say in f there are two separate equations, okay? F1 and F2, F1 and F2. And there are two variables in the state X, which means X1 and X2.
Yes,
is that clear? Okay, and let's see how we can calculate A. So for the first row, it represents the function F, the function F1. And for the second row, it represents function F2. And for the first column, it represents. Let me try to write something. Give me a second. I probably can write it here, right? So can you see my right? Oh no, it's not. It's not. Sorry. Probably I need to stop sharing. And I need to share the whiteboard. Yes, wait a second. Can you see the whiteboard?
Yes, sir. I can see.
Oh, okay, cool. Okay, so let's say we are talking about A is equal to, sorry, it's very hard to write it with the control pad. Sorry, this is F, right? It's F. This is X, right? And evaluate it as the equilibrium point. Right? And let's say F, it has two functions. Let's say F1 and F2. Right? So let's say we have two functions of the of F. So this is clear, right?
So,
and let's say we have an X, which also has two values, X1 and X2. Sorry, it's X1K, X2K. I make it simple. It's super hard to write. So That's okay, right? Until now.
If I understand, yes.
Okay, cool. Then let's see what we have for A. A is something like this. This element is row F1, row X1. All right. And this is row still F1. So each row represents one F divided by row X2. All right, and second row represents F2. Row X1, the first column is still X1. And then it's row F2. Row X2. All right, so it's a 2 by 2. It's a 2 by 2, right? The first element is row F1, row X1. The second on the first row is still row F1 and row X2. And then row F2, row X1, row F2, row X2. That makes things clear, I believe, right?
Yes, sir. Yes.
Okay, cool. So does that answer your question?
Yes. Is it the equilibrium point? Equilibrium.
Sorry, what's your question?
Is it the equilibrium
point? No. So this is equation. So let's say if F1 is equal to X1 square plus X2, let's say X2, right? Let's say something like this. And then row F1, that's the partial derivative. And row X2 is equal to 2 times X1, right? And then row F1.
Sir.
Yeah, sure.
It's equal 1 because it's derivative according to.
Yeah, that's right. That's right. And X2, that is equal to 1, right? Is that clear? And then if there's 1, you don't have to evaluate it, right? But if there's 2 times X2, because it's power, right? X1 power, then you need to evaluate the X1 at the equilibrium point. And that's it.
Can we just see the original question real quick?
Sorry, Sachin, what's your question?
Oh, just so for the F1 and F2 and also the X1 F2, in the original question, whereabouts do those come from?
Okay, so let's give an example. So I can try. Can I stop it? Stop sharing it?
Sure.
Yeah, I'll just take a screenshot of it real quick.
Yeah, so probably I'll share the screen is much easier.
Okay. No, I got it.
Yeah, so give me a second. Stop sharing it and share the screen. I'm sharing the screen now, right? No? Okay, yeah. Give me a second. All right, so you can see my screen, I believe, right?
Yeah.
So that is F1 and F2. So if you have two equations, X1 is equal to something, X2 is equal to something. That is F1 and F2. F1 and F2, they mean the two equations of F, the linear equation of F.
Okay. And what would X1 and X1 and X2
X1 means the X1, the first element of the state of state X, and X2 is another one. So in this case, you see you need to calculate F1 and row F1 or row X1, row F2, row X2, and put them into a matrix. And then you get the A matrix.
Okay. Right, that's how you find the A matrix. But then if you want to find the equilibrium points, then that's when you have to find the roots of
yeah, the roots of xk plus 1 minus xk equal to 0. Yeah, there we go. x1k plus 1 minus x1k equal to 0, x2k plus 1 minus x2k equal to 0. And then you solve those two equations, then you'll find the equilibrium points.
Okay, you find those 2 points, and then once you have those, and then you do what we just did before.
Yeah, when you have the equilibrium points, suppose you have 2 equilibrium points, and then you can do this linear. How to go? You can do this linearization. This linearization.
Oh sure. How can I know it's a linear discrete, or after linearization? How can I know it's linear discrete or linear continuous?
Yeah, that's a good point. If you remember, so in this case, definitely it's a linear discrete because it's xk plus 1 and sk, and there's no dot, right? So it's similar to distinguish which one is discrete time system and which one is continuous, right? So if this,
okay,
yeah.
So it's linear discrete because it's sk plus 1.
Yes. So yeah, what I mean is that the nonlinear case is discrete time system, and when you linearize it, it will be still discrete time system.
Thank you, sir. So it will be in the questions.
Sorry?
It will be in the questions, like it will show me like it's nonlinear discrete time system.
I can't say too much, but if there is a question and giving you a system, I'm not telling you if it's discrete or continuous. You need to find it out yourself.
Yeah,
and that's the first thing you need to do. If there's a question, that's the first thing you need to do.
Can you tell me the method for check stabilities of the linear discrete system?
Linear discrete time system. So the stability criteria is very clear, right? So if it's between -1 and 1, then that is stable, right?
Yes, sir.
Yeah, but I mean all the eigenvalues of A, they are between -1 and 1, then it's stable. Otherwise, it's not.
Yes, I mean the process of checking stabilities, like controllabilities also.
Controllabilities, okay.
Yes.
So controllability is first you need to calculate the controllability metrics. Do I have the? Do I have?
Hi, Liang. I have a question here.
Oh, sorry. Let me answer the question first. Where's the question first? Sorry, give me a second. Controllability. What is controllability? Oh, there we go. So you need to first calculate this controllability metrics, but normally calculate this. It's an infinite one, so you can calculate just a square one. That's fine, and then double check if it's full rank or not. If it's full row rank or full rank, then it is controllable. And this one is the same as the continuous one. So the criteria is about how to check the controllability of the system. Then discrete time and continuous time, they are the same. But stability, they're different.
I think this one is controllability of the linear discrete or linear continuous.
Yeah, they are the same. They are the same.
How about so the stability is different between continuous and discrete? I see. So it's
same. They're the same.
No, I mean taking the controllability is the same for both continuous and discrete, but
checking that as the same. Yes.
Yeah, but for the stability is different.
Yeah, that's a good point because the system is different. Yeah, I can't also directly about like why this one is the same but the other one is different. It depends on, I think mainly depends on different purposes. First one is the formulation of the discrete time system is different from the continuous one. And I think I gave a very simple example about linear discrete time system and linear continuous time system and how it can make it converge to 0, right? So so that is why the controllability, they are different. but the stability, they are different. But for controllability, we just need to use the state feedback control to control it, and try to find the proper K to make the pole placement to make it stable, right? But in this case, the process is more or less similar. So that is probably the reason why the controllability, checking the controllability is in the same way. Hope it answers your question.
Thank you so much.
No worries.
The controllability is based on the eigenvalue, the roots of eigenvalue.
Eigenvalues, yes. So that is from a mathematical derivation. So if you remember, we do have a very, very simple case. Very, very simple case. Let's say it's a for continuous one is a power k or something. I can't remember. And for discrete one is I think we have it here. Where is it? Yeah, here we go. It's a very, very simple case. I can't remember, where is it? Yeah, so it's showing that I mean, if it can be, yeah, here we go. So if we just have like a power k times x0, something like this, right? And if you have like different values of a, and it has different trajectories of the state, right? And then from the mathematical point of view, then if the eigenvalues, both the eigenvalues are between -1 and 1, then which means it's similar as you have a value between -1 and 1. Then the matrix calculating together is getting a converge to 0 trajectory, something like this. It's from the mathematical point of view. Yeah.
Yeah, thank you, sir. It's like taking the root of eigenvalue.
Yeah, something like that. Yeah, sure. Yes, sorry, Juan. I think I need to answer Sono's question first. Sono, did you have a question, right?
Yes, sir. Yes, sir. Thank you so much for your answer.
Yeah. So for the nonlinear discrete system, you calculated the A matrix there by partial differentiating it with x1 and x2. You differentiated f1 and f2 with respect to x1 and x2. But for calculating the B matrix, so we will be differentiating f1 and f2 with respect to u1 and u2.
If you have u1 and u2, then it will be in the similar way.
So
if you if you have u1 and u2, then you will calculate it similar way as A. But if you only have u, then you will have a 2 by 1 matrix, 2 by 1 vector.
But for that previous case, it will be a 2 by 2 matrix.
If you have u1 and u2, if you have two, yeah. If you only have one u, then it will be 2 by 1. So just remember, so for the dimension of the row, it depends on how many f you have, right? So you have 3f, then you have 3 rows.
So the dimensions should match with the final matrix.
The f, the functions, right? And for the columns, it depends on the dimension of the. Let me show you. Give me a second. Yeah, that's a very good question. Yeah, here we go. So let's say for A matrix, right? So the dimension on the row depends on the dimension of f. Let's say if you have like 3 functions for f, then you have 3 rows. If you have 2, then you have 2 rows, right? And the dimension on the column depends on
x1.
the dimension of x. Yes, that's right. So if you have 2x, x1, x2, then you have 2 columns.
Yeah.
Something like this. So similar to B. So let's say if for B you have like 2f, then it will be like 2 rows, right? Then if you have like 2 u's, u1 and u2, then you have 2 columns.
2 columns, okay.
Yeah, but if you only have 1 u, then you have 1 column. So which is 2 by 1 vector.
Oh, okay.
Yeah.
Okay.
Does it make sense?
Yeah. Okay, thank you.
Okay, cool. No worries.
I had a good question, just so that controllability again.
Yeah.
How do you determine the size of that matrix? I don't know if it was already answered.
Yeah, that's a very good point. Yeah, this is something I want to say. So normally it's an infinite matrix, right?
Yeah.
It depends on the value of t, right? But normally we just choose a square matrix. That's easier. Let's say if the dimension of B, let's say, is 2 by 1 and A is probably like 2 by 2, right? So in this case, you just have B and AB, and that's it.
Okay.
That's a 2 matrix already.
Is that just for everything? Just go for a square matrix. So just have B and AB, and that'll be sweet. Or
like
so how do you decipher which size to go for?
Yeah, so it depends on, normally depends on what's the size of A. So how many columns?
Oh, all right.
Yeah. So if you have like 3 columns, let's make it 3 by 3. If there's 4 columns, make it 4 by 4. If there's 2 columns, then make it 2 by 2. And that's it.
Okay. Okay. So controllability size is based off your A size.
Yeah, but normally, I mean, you can calculate more, but it's calculating it's calculating row rank.
Yeah.
Right.
Okay.
Yeah, but anyway, so for simplification, you just make it a square matrix. It's easy to calculate the rank as well, right?
Okay. I also had another one as well. I'm just doing a question with where is it? I'm just doing the triangulation one again.
Yep.
1 second. Let me just find it. Yeah. Do you want me to share my screen?
Oh yeah, sure. Give me a second.
Because I got my solution here, but I just want to make sure I haven't done anything dumb. Okay, yeah. So here's the question. 3D point in left camera frame.
Yep.
So where is it? Let me get my working up. Can you see that one there?
Yep.
Yeah. So hold on. Yeah. So I've written down all the stuff. 3D left equals question mark. So when I'm solving like Z, Y, and X, say, is this kind of the right working out? Because I did the left projected, right projected, which I don't. Actually, no, I do need it for the Z. Like, is that all right? I don't know.
I think so. Then you have minus 100, minus 200s, right? And then you have 100 in there. Yeah, I think that's right.
Okay, so and then if say the question asked me to do from the right, say from the right projected, would I then switch around XR and XL for this section?
No, always XL minus XR.
Always XL. And then for X and Y, I would have this is XR instead?
Yes. Sorry, wait a second. Here it depends on like which coordinate frame you're going to have for your 3D point. So normally I'm asking you to have a 3D point in the left camera coordinate frame. Then you use XL.
Okay.
Yeah.
Oh, so the question asking for
so always
3D point in left camera frame is XL, and then say 3D point in right camera frame I use XR.
Not that easy, I think. Not that easy. Yeah. But anyway, so normally what we do is always calculating the 3D point in the left coordinate frame.
Okay.
The left camera coordinate frame, and then if you want to change to the right, so probably it's just a offset, right? You change with the offset, and that's it.
Yeah.
After it gets 3D. Yeah.
Okay, so how would I do that offset then if it was to the right?
Okay, so for example, I'm asking the baseline is what's the baseline here? It's 0.2. 0.2. And then let's say the baseline is only on the X coordinate frame.
Yeah.
Right. And then if you want to calculate the position on the right coordinate frame, then you you make the current XYZ, then minus 0.200, and that's it. Right. So it's just offset.
Oh, so I would take the coordinates I get here down the very bottom from the left coordinate frame.
Yep.
I would minus the 0.2.
Yeah, 0.20 and 0.200.
0.200. Okay.
It only has offset on the X, right?
Okay. And how would does it change? Is it sometimes positive, sometimes negative, or is it just always minus the baseline?
Hey, it's a good point. So let's say it's the camera coordinate frame, right? So camera coordinate frame, which the z-axis is just from camera center in front, right?
Yeah.
So sometimes you observe the feature on the left side of your image, then you get negative 3D point. If it's on the right, you will get a positive. So yes, the xy can be positive or negative, but z must be positive.
Yeah. Oh, okay. Yeah. And then
because the feature need to be in front of the camera, right? Yeah.
Okay, and then just always minus the baseline then from your left frame.
Yeah.
Okay, cool. That makes a lot more sense.
No worries.
Thank you very much.
No worries. And Joshua, sorry for waiting.
If we get a theory question, how do we know how many points we need to kind of write down? Like, let's say we get a question that's talking about feature extraction between like SIFT and SURF or something like that. How many like kind of points do we have to do per mark?
So it's like short answer questions, right?
Yeah,
something like
yeah.
Explain something. Yeah. So probably write as much as you can, we mentioned. But when we mark on that, normally we just get the like bullet points.
Okay.
Let's say what is the try to explain what is SIFT.
Yeah.
Right. I think the first thing is you need to mention SIFT has two parts, right?
Yeah.
One is feature extraction, one is a descriptor, right? For matching, right? And the second point probably explain it how to get feature extraction. Is the Laplace transform of Gaussian, the difference of Gaussian to calculate maximum and minimums of the Laplace difference of Gaussians, right?
Yeah.
Something like that. And then for descriptor, explain what is descriptor. Right, that has 128 dimensions, and calculated from the histogram of the gradient, something like this, and you get all the points, right? So try to write as much as you can, but we always like mark with like the bullet points.
Yeah.
The juicy part of like of your explanation, something like this.
Yeah. Sounds good. Okay, thank you.
No worries. Yeah, I'm here.
Yes. I want to ask you about solving. So
video serving. Yep.
Yeah. So I have the velocity of the.
Sorry, I can't hear you.
So in the part of the visual serving, in the coloration, so we have the part of like calculating the velocity, but it doesn't have the result there on the slides.
Sorry, I can't get your question. Sorry, can you repeat it again?
Can I show my slide, sir?
Oh yeah, sure. Yeah, please share your screen.
Okay, so yeah. Oh no, please. 1 second, sir. Let me turn on this.
It's video serving, right? So it's next lecture. Yeah.
So I understand all of it. So
yeah, video serving. Yep. And
so we don't have this answer for this.
Oh, great.
Velocity here, sir.
Sorry, is it velocity or the, so what's your question? So is it
Yeah,
calibration? Okay.
I don't know how to answer the questions.
Oh, right. So we have a code, just run it and get it.
Oh, really, sir?
Yeah, I have a code there. So just run it and get it.
Tutorial, yeah, right?
Yeah, I think it's in the it's in Canvas, in that module. Yeah, we
It's
do have
called,
a code.
I think it's called VSM. Yeah.
That doesn't anything much.
That's a
There
sub
should be
function.
another one.
You mean this?
Yeah.
Thank you, sir.
No worries. Yeah, probably have a look, have a run on the code, and probably have a look what code implemented. Yeah.
I was just gonna ask about that question, Liang.
Yeah, sure.
The one that we just looked at then. So it looked like you just have to add 50 to all of the numbers for the observation.
Yeah.
That's what he's telling you, right? Okay.
Yeah. So it's kind of like just simulate what's the what we the desired position is, right? Or current like position of the feature is. Yeah.
Okay. Yeah, and I thought also for the exam it was mostly focused on the actual practical, like doing the number questions, not so much like the knowledge stuff. But
yeah, I can't say too much about what we have in the
sure.
It's 30%, 2 questions, and with sub questions, something like that. Yeah. So we are not having any experimental like things like calibration. That we definitely don't have that, right?
Yeah.
So we don't have computer experiments. We don't have that, and so normal is from the lecture notes. Then if you review it and if you can solve all the examples and also the activities by yourself, then probably there's no issue with that. That's my feeling.
Okay.
Another quick one.
Yeah.
Just with the question I was showing you before with the thready points and the left coordinate frame, right coordinate frame.
Yep.
If you minus the baseline from your left coordinate system, you go further into the negatives on the x-axis.
Yep.
Wouldn't that mean it's going more to the left instead of to the right?
Yeah, that's a good point. Let's say something like this. So if you have a point just in front of you, which means your x is 0, right?
Yeah.
And you move yourself 1 meter to the right.
Yeah.
It becomes negative in your system, in your one, right? So it becomes on the left of your in front, right?
Can you repeat that again by any chance?
Oh yeah, sure. No worries. So let's say you have a point just right in front of you.
Yeah.
Right. So that's 0 axis. Sorry, that's 0 on x, right?
Yep.
And then if you move on the right, let's say step on the right for 1 meter.
Yep.
The point is not in front of you anymore, right?
Yep.
It's on your left. It's on your left.
Oh, okay. Yeah. I get you now.
On your left means negative, right? So you move your system right, then which means that the points move to
the point is -1 to the left.
Yeah. That's right.
Right. Okay, that makes sense.
Yeah, no worries.
All right, thank you.
No worries. Yep.
For the so we don't really need to study the Harris corner, right, sir?
I didn't say that. I can't say too much on that. I'm sorry. I can't say that you don't have to look at this part, you don't have to look at that part. I can't say.
Yes, but I want to ask you 3 questions.
Oh yeah, sure.
I want to ask you about So we have the extraction and tracking. So we have the serve and the shift. So
yeah,
is it should be in the slicer, or we have to research it outside, like theory questions about this?
All right. So anything, I mean, if we're asking about safe and serve, if
Yes.
there is a question about that, I'm not asking something outside the lecture notes.
I mean, if you told me to explain everything, so I think from the lecture is all right, or I need to put more additional information.
Everything from lecture note is fine. This is what I mean. You
Yes,
don't have to.
yes.
You don't have to like find the original paper and write it in super details. You don't have to. Just everything we mentioned in the lecture notes. Yeah, that will be enough to answer the question about safe and serve.
Thank you so much. I just want to
No
read
worries.
about this because theory, I think, is really diverse. So I can.
I know. It's a lot of things. That's why we didn't like introduce too much on those. Right, I'll just give you a brief idea about like what are those like feature extraction matching methods and what's the things roughly behind. But if you look at the original paper, it's so complicated. And if you're interested, you can read on it. But I mean, from the subject point of view, we just want you to understand roughly or the basic ideas behind those feature extraction and tracking and let you to use it.
Thank you, sir.
No worries.
I want to ask one more question, sir.
Yep.
Also, we have the gradient magnitude, the edges of the picture. I mean, the norm. So do we need to like analyze everything, or just write in the formula and push the result there, or we have to write the number down on the exam?
Sorry, I didn't get your question.
I mean, so if I give you the general formulas, but I didn't write the number, I mean the process, only the general number, and I got the result in MATLAB, can I just put there? I mean, for example, so we have the formula for the gradients, like the norm of the image.
The gradients, right? Yeah.
So I put it in MATLAB. So I write the formula, the general formula, like the general formulas, but I didn't write the numbers to get to the results. I only write the result. Is it all right, sir?
I think it depends on the question. I can't talk too much on that. I can't say like we have that, we don't have that or something. But I mean, if there's a question asking you to calculate the gradient.
Yes.
All right. So if I'm asking, please calculate with the number, please calculate it, then probably I need to get the number. But if I'm just saying, please explain, let's say explain what is Harris corner detection, or please explain what is SIFT or SURF, then you don't have to do any calculation, but you have to write the bullet points, the major messages of each of the question with necessary equations, and that's it. So it depends on what's the question, right? So if the question is a short answer questions, just ask you to explain, then you just explain. You don't have to do any calculation. But if it's calculation, I'm asking you, let's say, what's the triangulation, what's the XYZ, right? Then you have to do the calculation, something like this.
Yeah, thank you, sir.
No worries.
Just a quick question about the Harris corners as well.
Yep.
The equation that we use, the one that has the like the ix squared and the ix iy.
Yep.
That one, to actually calculate that, the values for the ix and the iy, would you just say, the question might say like, here's 2 points and here's the values of their the darkness level at these 2 points, and then like from those you would calculate the ix as the difference between the darkness level of those two, like those 2 points? Is that like how you would do that? And you do the same for the y?
I can't say too much about the question if there is or something. But I mean, if I'm asking you to calculate something, and I have to give you necessary information for you to calculate, and I'm going to make it very clear about what you're going to calculate.
Okay, because I was just confirming basically that like the IX is like the difference in
in X. So in X, so it's the gradient in the X direction. So normally we just difference it. For example, if you use the one on the intensity of the pixel on the right minus the current one, and that's it, right? So that's the gradient. That's easy way to calculate the gradient. But sometimes they use +1 -1 to do the gradient. But anyway, so either way, I'm happy. Yeah.
Okay, and that gives you, or it should give you a matrix that has numbers on the diagonals and zeros in the other spots, right?
Sorry, what's that case?
Like when you evaluate that matrix, the one with the IX squared and the IX IY, so on.
Yep. So you have the second moment matrix, right?
Yes.
And so normally you will have like different values at least on the two diagonal ones instead of two diagonal elements. Yeah, but I mean, if there's a line, so normally we will have only one value. I mean, one non-zero value on the diagonal, something like this.
Yeah. So like, there should be numbers on the diagonals, and then on the other values in the matrix, it should be 0, right?
Sometimes it is, sometimes not. It's hard to say. Sometimes it's, sometimes not. Yeah.
But you only really care about what's on the diagonals anyway, because that's what tells you if there's a corner or not.
Normally it's like that. Yeah.
Okay. All right.